I'm going to talk, Robert talked about sort of very fine-grained parallelism and then a lot of the broad concepts. I'm going to talk about sort of slightly less fine parallelism, meaning data parallelism, so shared memory, threading, and then tomorrow we'll go on to more coarse parallelism. So one of the things about shared memory is it's easy because you could just access data. You don't have to think about how you get to data as you do in MPI, like send, receive, or read, write, or whatever it is. But on the other hand, because everyone can just access data, you have something called data hazards and race conditions. So I'm going to start with a little CS gobbledygook because I actually work in CS most of the time. There are two models of parallel computing. This is just FYI, you could read Wikipedia if this interests you. One model is CSP, communicating sequential processes, and that says, you know, we're all people and we talk to each other, and then sometimes we don't talk to each other. We're sort of communicating sequential people. And then there's this PRAM, which is parallel random access machine, which basically says you have a whole bunch of independent execution units, but then you can just randomly access any part of the machine. So if you read the PRAM Wikipedia page, as I did last night about 3 in the morning to remind myself, it refers at the very top to conflict resolution strategies. So you know, when you share, you have to deal with the fact that you have to take turns, basically. And the ways of how you take turns with data to ensure correctness and good performance. So the MPI zealots that I work with will argue, you know, one of the reasons that MPI is successful is because CSP is easy to reason about. When we talk about it, it is very easy to think about the dependencies and the problems that can happen in MPI programs. You can hang yourself, you can deadlock your programs very easily. But when you think about data, the memory model, and how you access data, the correctness requirements are fairly straightforward. Whereas models that look more like PRAM, which is like PGAS programming language that you may have heard about, and multi-threading, of course, is more like PRAM. You tend to have very, very subtle, nefarious bugs, Heisenbugs, where you run it one time and you don't see a problem, and then you run it the next time you do, and it's because, you know, basically PRAM doesn't give you a lot of guarantees on its own. Okay, so the reason, so this is introduction to race conditions. So that part of the problem is that when you write code, you don't see the hidden operations. So if you say you want to write x equals a plus b on a computer, you might write variable x equals variable a plus variable b, and then semicolon. But what you actually get isn't that. You get, the computer will generate code that says, load from the memory location that was indicated by variable a into a register. The register is the sort of tiny little workbench of the processor, and they'll do that for b. And then in the registers, it will actually add the register 1 and 2, which contain the data that was in a and b, but it's now a copy. It's not, you know, it's not locked the data. There's no, you know, other than what's provided by the hardware as part of the design. I mean, register 1 has a data element, and memory location A has a data element. They happen to be the same, but they're actually separate data elements. And then you add the 2 registers into a third register, floating point unit or the integer unit does this, and then you store that register to a memory location. So the register computation, the add here is, for all practical purposes, infinitely fast. Okay, I mean, it takes 1 cycle, but there's nothing, you can't talk about anything taking 0 cycles, so that's infinitely faster computer. But 1, 2, and 4 actually take a finite amount of time, and in fact can take a long time. So, you know, if you do this on 2 threads, what happens? And a thread is, in my definition, I mean, something that has its own registers, generally speaking, or at least all threads have registers. Even if 2 threads share a set of registers, they have their own virtual registers. So, what's a race condition? So now I have 2 threads, and they're both going to compute x equals a plus b. And I'm going to name the registers R and S so you know that they're different. So, load, add, store, and over here you load, add, store. Sorry, that's a typo, that's an S, okay? So over here you've got thread 1 we're going to register as R, thread 2 we're going to register as S. So when you do this, x equals a plus b have 2 threads, what's the value in memory location x when they're both completed? Was it the value from register R3 or S3?
Sort of finished last.
Yeah. And then, so in this case, does it matter? No, because they both loaded the same input. I mean, unless one of them got computed it wrong, which we're not going to talk about wrong computing, although someday we will. Okay, so it doesn't matter. All right, so now I changed the input. So now thread 1 does A and B, and thread 2 does C and D. Again, this is S3. So now, do we know what the result is? We know it's whoever finished last. And it does matter now, because unless A plus B equals C plus D, and you're out, well, for all cases of A, B, C, and D that you could possibly generate and you put in your program, it does matter. So you will get one value of X for the case where thread 1 finishes first, and then another value of X for the case where thread 2 finishes first. And you have no control, right? Thread 1 and thread 2 just do their thing. They're concurrent, okay? That's what threads are. And so you should read about this because I probably shouldn't belabor it too much, but there's a difference between concurrency and parallel. So parallel sort of means like multi-core is parallel, but threads are concurrent. So concurrency can happen in a time-sharing way even on a single core. So there used to be time-sharing servers, and like 20 people would run on one processor and they would just time slice. So the thing about that is, it isn't just parallelism that gives us race conditions, it's actually concurrency, because you can have a lot of these data hazards actually come out from instruction level parallelism and pipelining and compilers, which is a single thread of execution, but the compiler can reorder instructions, and that's where you get data hazards. So the fact that you have threads means you have this problem. It's not just if you have multiple cores. So if you have 2 threads running on one core, that doesn't mean that thread 1 runs first and thread 2 runs first. It means they're both running and the hardware is going to take, and they're going to interleave however they feel like interleaving, and that isn't in it. There's no requirement that that be deterministic. So that in that regard, you don't have any way to know what X will be. All right, so now I change it one more time. So now I have 2 different input sets, but I have 2 different outputs, X and Y. So now do we know what X is going to be? And we know what Y is going to be. And that's good, right? So we can run in parallel, we can run it concurrently, and we know what answer we're going to get. And it's always going to be the same because we now have independent outputs, okay? So where you read from and where you write from matter, and of course, if you could read from 2 things in parallel, like in the beginning when we were reading from the same locations, it was okay, there wasn't a problem, but when we write to the same location, we have a problem. We can fix that by writing to separate locations. So, in categorizing data hazards, and Wikipedia has this for pipeline, but I tried to find a good resource for threading where it changes the definition, and I didn't, so I just make up as best I can. So what we just saw was a WA right after write dependence or data hazard, which means 2 different threads we're going to write to the same location, and one of them is going to blow the result of the other away, and therefore we don't really know what the answer is going to be. The other thing you can have happen is in terms of granularity and atomicity. If X was an array, then 2 threads could be writing to an array, and array writes are not atomic, so you could actually get a linear, basically the superposition of X depending on how they write, and depending on cache line granularity and atomicity and all these things, you can end up with just totally bogus result. One of the things that, there are some programs where you don't actually care about what X is, as long as it's one X or the other, and you just don't want crap, okay? So especially if you have sub-word level So word is like a double precision number. But imagine you have a complex double. So it's a 16-byte type, and you're running on hardware that has 8-byte atomicity. And you want to just store the result of some complex operation. 2 threads do that. You can get the real part of x1 and the complex part of x2, and that number may just be physically invalid. Where if you at least got one or the other, you'd be happy. So so there's sort of more complexity once you get to beyond just the basic data types. And then there's raw and war, which in this case really just mean you make an assumption about the temporal ordering of a read and a write, and you don't get it. So if I'm expecting an output from somebody before I start my computation, and I jump the gun and read it before I get that result, I'm not getting the right result. It may be okay, it may not be okay, but I'm not getting the result I wanted. And in the same regard, you could write, right after somebody else has read. I mean, it's fairly obvious to work these out for simple mathematical operations. You need to read the data not just at the right place, but at the right time. So obviously you probably segfaulted once or twice in your life, you've overran memory, you've done out-of-bounds array access. Fortunately, operating systems and compilers and debuggers are good at detecting sort of spatial out-of-bounds, but there really aren't any general purpose tools to find sort of temporal out-of-bounds to say, oh, sorry, you did a load before you meant to do that load because I know that you want to store and then load. Nobody knows how to make that automated. So you really have to think very, very hard about this yourself. So, and that shows how well I can count. 3 good ways to avoid data hazards. So one thing you can do, and I know Robert's a big fan of atomics, and basically anybody who does anything with current currency loves atomics. So atomic operations, you guys fortunately are chemists, so I hopefully don't need to talk about what, atomos means indivisible. So an atomic operation is an indivisible operation. So it means that if you do an atomic add, you do the load, the add in the register, and the store, you do that either all or nothing, okay? And so now, the expense of that can be substantial. So you can do a regular old add in like 1 cycle. If you want to do an atomic add or fetch and add, it might take 100 cycles on some architectures because you're doing a complex operation that ensures correctness. So now, bad news is it takes 100 cycles. The good news is you can actually write a correct program with it, because if I wrote the program before and I could just put this is atomic over the load, add, store, and if I could just put a bracket that says, hey, this is atomic, then that program is safe. There's no race condition there, because I'm either going to get X or I'm going to get from one or X from the other. And especially if I was doing fetching, where I was taking an output from one and putting it back in, I would know that I could get an intelligible operation. So if you do a reduction, right, you want to sum dot product style a whole bunch of numbers, and you want to do a threaded reduction. I mean, atomics are not the right way to do threaded reduction, but one of the ways you could do it is you could just say all of my fetch and adds happen atomically on all the threads, and so they're all just adding up the result in such a way that you correctly take whatever the result was before and add to it, rather than having 2 threads load and add their result and then basically blast each other. So the other thing you can do is you can impose some form of critical section or mutual exclusion, which is sort of a generalization of atomicity. So atomic operations, as I'm defining them, are sort of what you get from hardware. They're at word granularity. You can do an atomic add on an integer, but you can't do an atomic, or at least on most architectures, you can't do like an atomic linked list update or an atomic matrix transpose, right? If you do matrix transpose in place, you need to load and then store into the same memory. If you do that in parallel, you get all sorts of garbage if you're not careful about it. So you put a critical section. You can just say this thing in this block has to happen all at once, And then you don't care about the ordering, but you do care about the all-at-once property. And those are expensive. I mean, we have hardware transactional memory on BlueGeneQ that was supposed to make this magic, and it turns out that doing it in software with human intelligence always wins, although lots of people have written papers claiming it's magic. Anyways, there's a lot of magic out there that is meant to replace thinking and doesn't. And then the other thing that you could do is you could sort of do controlled synchronization. So you could say, let's explicitly take terms, right? So we have this data element X, and if we all need to write to it, I could just say, oh, here's a baton. You have the baton, you can touch that memory location. You don't have the baton, wait for the baton, right? Well, imagine how long it takes us to pass the baton around the room while we all change the memory location. So that could be extremely expensive, but it might actually not matter, and you might really care about performance. So these are sort of not all the ways, but this is 3 different types of ways to do it. And if you basically, you'll understand how important it is to avoid mutual exclusion by just looking up lock-free algorithms. And you will find tons and tons of lock-free algorithms because people know that locks are expensive, and doing certain types of serialization are hard or expensive, and so you want to have lock-free memory allocators that use very, very fancy atomic operations and things like that. So people who care about performance are going to pay attention to that. Anyways, so there's something else that happens, which is that the computers don't actually act at word granularity. They act at cache line granularity when it comes to DRAM. And on a machine like BGQ, you actually have a 64-byte cache line from L2 to L1 and a 128-byte cache line from L2 to DRAM. But we don't have pages. But pages don't matter in terms of granularity as far as I know. But what it means is you're going to store a cache line. You're going to load a cache line into cache, and then you're going to load an element out of a cache line into a register. And so what this means is you now have to think, even if you say if x0 of an array and x1 are on the same cache line, you might not have a true race condition because you can write to them independently. But if you load the cache line into 2 different processor caches, and then they both change a word and then they both write, you have to have conflict resolution. Now, I didn't actually do enough to look up. I think x86 mediates this, right? You don't have a problem with false sharing leading to correctness in x86, right?
Yeah, there's no correctness issue, but it's a big performance issue.
Yes, okay, so there's 2 issues here. So on x86, which will be the dominant platform that you guys will use, it's not a correctness issue, but you'll get terrible, terrible performance if 2 threads are running the same cache line, because they'll just they'll fight over it like a couch. So it's like, you're on your couch with your brother and you're fighting over the remote. Even, you might be like, don't touch me. And you're like, I'm not touching you. Well, you're in my space, right? So it's like you can't, you're not even actually sharing the same space. You're just sharing the region of space, and yet you're still fighting over this. I'm thinking about these things because I have a 2-year-old, and I'm soon going to have another one, and I know that they're someday going to drive me insane by fighting over the couch like this, just like I did with my brother. But anyway, so I don't actually know if this is a correctness issue on weakly consistent architectures. I should just test it this afternoon, but there might be an architecture, in fact, if you don't have cache coherence. So fortunately, you guys haven't programmed a non-cache coherent system with BlueGeneL, the Intel SCC. There's some other architectures out there where this would in fact be a problem, because the fact that you have the same cache line in 2 different caches, there would be no coherence between them, and therefore one processor could change a value in this cache line and another processor could change a value in this cache line, and they don't know about it, and then they store a cache line, and then you get them blowing each other away. So I think on the Intel SCC that would be a problem. And like I said, you can get these data hazards even if you're time slicing. You don't necessarily have to be on a multi-core. Okay. So I'm just going to define data parallelism. So I spend too much time at lunch on fail blogs, so I see all this idiotic stuff that people do in the world. So the trivialist form of data parallelism, so basically a for all construct. So for all data elements do something to it. So a way for us to epic fail together is we could all go to a tattoo parlor, and for all of us, we could get YOLO tattooed on our arm. That's, you know, but, and the thing is, depending on which font you choose, it might take a different amount of time, but the fact is, we're all getting YOLO tattooed on our arm. That's data parallel. The fact that we're really uncoupled, other than that, you know, if there's infinite tattoo artists, it doesn't matter. So this is, that's basic data parallelism. BLAS is all data parallelism. You just say for all elements of an array, do something to it. And you know, data parallelism is extremely powerful up until the point where sort of it runs out, and it runs out in a couple different directions. So we're not going to talk about it here because it's an advanced thing, but if you want to see sort of just how easily it is to run into the limits of data parallelism, you can look at LAPACK, which I guess you guys heard about last week. But basically LAPACK is built on, if you want a multi-thread LAPACK, you're sitting on top of BLAS, which is data parallel, and you basically just do data parallel, data parallel, data parallel, and it turns out that doesn't actually thread very well. So if you do threaded dgem, you will scale all the way out to all the threads pretty much for a big enough matrix all the time. If you call threaded dseyv, whatever the eigensolver is, you'll find that that doesn't thread nearly as well. If you do threaded Cholesky, it won't thread nearly as well. And it turns out that the way Cholesky and eigensolvers work, they don't have full breadth data parallelism all the time. You're doing Cholesky, you're sort of doing these panel ops, and you have more parallelism at one point than at another. And data parallelism doesn't allow you to sort of balance the fact that you run out of parallelism. You want to go change the granularity and things like that. So this project, Tennessee group has this Plasma, Magma, and so Plasma is like multi-core, Magma is GPU, and Dagway is a DAG scheduler. They renamed it Parsec, but Parsec is a triply overloaded term. You'll have to be very, very careful with Google to find Parsec, because there's a Berkeley electronic structure code named Parsec, and there's a Princeton multi-threaded benchmark called Parsec. So even if you type in a whole bunch of keywords, you still get the wrong thing. But anyway, so Dagway is a DAG scheduler, which is really implementing task parallelism. And there's a similar project out of Texas called Flame and Supermatrix that does the same thing. And they're trying to go beyond data parallelism in dense linear algebra. So dense linear algebra is sort of like the low-lying fruit of data parallelism, and yet even already that's having issues. So this should tell you that data parallelism has a lot of limits. And in a lot of ways, the way LAPACK uses quantum chemistry, or LAPACK uses BLAS, resembles the way a lot of quantum chemistry codes use BLAS. And so, you know, I actually, when we were doing the GPU and multi-core coupled cluster stuff, we looked at a lot of this literature to try to understand how to get beyond data parallelism in our codes, which was really valuable. Okay, so interesting data parallelism. So how many of you are quantum people? How many of you are classical MD people? One? Okay. No, that's, you will make more money than, if you do classical MD, you will make more money than all the rest of the quantum chemists combined. Or at least get 100 times more supercomputing hours anyways. We get a lot of, NAMD people use our machine like crazy. But anyway. So if you're a quantum person, I hope you know something about this, you know, generate all the Coulomb integrals for IJKL in the shells, compute the 2-electron integral. I'm sorry I butchered that. I was trying to write in some sort of fancy algol style notation or whatever. So I was reading the Minnesota, like Kumar Kaipuris book last night, and their definition of data parallelism is really SIMD, simultaneous instruction, multiple data, and it doesn't actually permit dynamic load balancing or non-global data redistributions. Now, global arrays and OpenMP are, in my opinion, mostly data parallel, or at least express data parallelism among other things. They aren't so restricted. So they're sort of SPMD, single program, multiple data. You can sort of, you don't have to be on the same instruction. But the thing is, if you take the former definition, so there's a, you know, the quiz. So why is this a problem? So if you do pure data parallelism, you just say for all IJKL, generate the 2-electron integrals. Why might that be an issue? Why might there be a performance issue with that? So what do you know about the two electron integrals? So the symmetry, how about computational cost? So SSSS versus FFFF.
Yeah, the cost increases with the angular momentum.
Yes. Well, and then how many word outputs come out from a 4S integral? 1. How many from F? 4Fs. 7 to the 4th minus permutation symmetry or whatever you want to apply. Okay, so what does that mean? So compute V is going to vary in its data footprint, and it's going to vary in terms of its flop count and memory count, therefore its execution time. So if you really say there is no dynamic load balance, and we just loop distribute these things over threads, we're going to have, let's say one thread gets all of the, 4S, and it turns out 4S can be, the compute intensity can be really high. If you have, let's say I'm using a basis set with 750,000 primitive Gaussians contracted to one, contracted Gaussian. Okay, that's ridiculous, but how long is a quadruple S integral going to take if I'm contracting 750,000 primitives? It's going to take eons compared to a 7F. So this is a problem. So you need to have some way to dynamically load balance. How about you said symmetry, same sort of issue. So what happens in Schwartz screening? Anybody know with the two electron integrals? So there's a Schwartz inequality. If you know undergrad linear algebra, it allows you to get an upper bound on two electron integrals ijkl from just ij, and that you can then screen. You can say, oh, I only want to compute DFT to its physical accuracy, which is basically like 0.1 Hartrees or something. Or I like to make fun of DFT. Anyway, so you want to compute a very low accuracy or whatever. You want to screen out lots of integrals. So there's branching in there, because you'll say if this integral is likely to be significant, do it. Otherwise, keep going. Well, in a pure SIMD concept, you can't have that thread divergence. And part of the reason I mention this is because GPUs have this issue. So you can't diverge warps on a GPU without running into serious issues. And if you look at what like Todd Martinez does in his integral code on the GPUs, one of the things they do, which is really interesting, is they totally reorder how they traverse the shells in such a way that changes the Schwartz inequality. So they sort of sort them in a different way than they're traditionally sorted, and this allows them to get more they don't get as much thread divergence. Turns out that there's nothing novel about that for a GPU. It also helps on a CPU. It's just that they don't like to backport any of their optimizations to CPUs. Same thing is true for MD range cutoff. So if you do molecular dynamics and you want to cut off, say 100 angstroms or whatever, to try and keep the cost of your potential cheap, you're going to have this divergence too. So you need some notion of just beyond SIMD in these types of computations. So now I'm going to talk about OpenMP. I decided that there's a couple. So David Sherrill has an OpenMP tutorial that's very good on his website. It'll be, since it's public, I don't think there's any issue. It's going to be in the repo once I can upload it and make it public. And there's another tutorial. You should Google this. It's LLNL OpenMP. It's a Lawrence Livermore National Lab OpenMP tutorial. It's fantastic. It is my absolute #1 go-to resource for OpenMP. It has everything on it. So I'm not going to cover everything. I mean, I could just go through every single construct and show you an example, but you should just learn that this afternoon by writing code. So I'm going to go through what I think are more the conceptual parts of OpenMP. So Robert talked about this. So OpenMP is directive, so it's language extensions, and it doesn't affect the code if you don't have compiler support. So it's sort of invisible unless you want to use it, and you can, if you have, some compilers will whine about it, but in general, especially if you do Pragma or IFDEF guard, then of course you can just turn it off and turn it on at your leisure. It's perturbative, so you could take a code and with a bunch of caveats, but at least in procedural Fortran code without enormous amounts of common blocks, you can just locally add OpenMP and just keep marching along. So you take your 40-year-old Fortran code and you can just add OpenMP to it, which is a nice thing. In contrast, if you want to do pthreads or TBB or some of the more task-oriented models, your code has to be somewhat friendly to them, or you have to do some adaptation to get that to work. OpenMP is extremely portable. There is every compiler that you guys have access to except one has OpenMP support. If you're on a Mac, if you use the GCC front end through Dragon Egg with the LLVM back end, you're fine. But if you use Clang, and you only use Clang if you're a C, C++ person, because their Flang is not yet ready. So Clang is the C front end for LLVM. We don't have OpenMP support yet. So a colleague of mine is actually working on both the Fortran and the OpenMP support in that, and I may be writing the OpenMP runtime or adapting it for LLVM soon enough. So in the future, there won't be anybody who doesn't have it, but for now, it's really quite portable. And it's straightforward. OpenMP makes simple parallelism really easy. It doesn't necessarily make complicated parallelism easier, but a lot of people just want simple parallelism, and OpenMP definitely provides that. The major problem with OpenMP is that it really doesn't have any first-class support for data, and you can get all sorts of problems because OpenMP just says, oh, shared memory. What's the difference? Memory over here, memory over there, caches. I don't know anything about these things. Different memory controllers. NUMA, never heard of it. OpenMP doesn't care. And I'll show you an example where it's one of the things that we have this guy who's a retired nuclear physicist who works like 80 hours a week. He's crazy. He gets literally doesn't get paid, but he works 7 days a week because we know if our machine goes down, we know within 2 hours because of this guy. And he's totally obsessed about performance, and he reported this. He'd been running on BlueGene, which is a true UMA, Uniform Memory Access Machine. He wasn't seeing any problems, and then he switches over to the Intel dual socket box, and I'll show as the last example exactly what this is. But he said, oh, this doesn't work the way it's supposed to, and it turns out that you have to actually zero out your memory in parallel in order to get maximum performance, or at least better performance than if you don't. So there's some problems there. So hello world in OpenMP. So OpenMP has a few runtime calls, but the really fundamental thing is this pragma OpenMP parallel. So this defines a parallel region. And I think if you look at example code of like parallel 4, sections or whatever, you think that pragma OpenMP parallel is just sort of this decorator that says, okay, now I'm doing parallel. But there's a lot more to it, and I'm going to belabor it because it's important, because there's a lot of stuff going on here. So let's first contrast. This is a serial region. There's not, if you call get thread num, which is just which thread am I, and get num threads, which is how many there are. This runs in serial. So the output here is one line of I am 0 of 1. Now you hit this, OpenMP parallel. So what happens when you hit OpenMP parallel? If you haven't hit it before, this creates the OpenMP thread pool. The runtime will, so don't ever time your OpenMP code. Don't ever put the timer around the first call to it. I mean, most scientific codes are going to go in and out of OpenMP many, many times. You're not writing a 100-line program to do science. If you time the first OpenMP parallel, it's going to take a while, because it's actually OS is going to have to spawn threads, create stacks, move all these points around. It's going to do that the first time, and then those threads are going to be a persistent thread pool. They're going to be sitting there in the background. I'll also say the same thing is true for a bunch of libraries. I had a friend of mine timed DGEM with GoToBLAS, and he was like, it takes like 1 second. And it turns out that GoToBLAS chooses to allocate like 200 megabytes in the background in some systems, which isn't a bad thing, because with virtual memory, it doesn't actually steal the memory, but there's a bunch of things you should never ever time the first time through, unless you really want to care about running over it. So if you do this, and this is wrong, it should say parallel, I'll fix the code. What do you see? You see I am 0 of, on my machine it's 8, I have 0 of 8, 1 of 8, 2 of 8, 3 of 8, 4, you see 8 lines for all the threads reporting back. And of course, they aren't ordered because there's no construct in this parallel region that says they should be ordered, okay? So the interesting thing about, this creates a thread pool, and now you can have, how many threads you have and which thread you are. This is actually an extremely powerful construct. So I have a student right now who's running a parallel linear algebra library, sort of a successor to GoToBLAS. And this is the only parallel construct he uses. He doesn't use parallel for, he doesn't use sections. The reason he uses OpenMP is because it is a nice, easy way to manage a thread pool. And then once he does OpenMP parallel, and he has the thread ID, he knows what his thread team looks like, and he does all the control for parallelism by hand from there. And he's like, basically it's easier than writing pthreads code. So there's nothing that says you can't use parallel as just a way to create threads in a portable way. Now pthreads is super portable except to Windows, which please don't tell me anybody programs in Windows, it's terrible. But in theory, OpenMP might be an easier way, particularly if you're in Fortran, right? So pthreads doesn't have Fortran support. If you want to have a thread team in Fortran and you want to do something with that you don't need parallel for or whatever for, then you can actually use this. And this thread pool will stick around, and in some cases I've heard it busy polls, which is the worst thing ever. But in HPC, some people say latency matters more than everything else. And honest, to be perfectly honest, parallel do and parallel for are syntactic sugar at this point. Because there's nothing that says that you can't take all of your do loops and chunk them by hand based on the thread ID. If the loop goes from 1 to 1,000,000, you just say, oh, divide it up by num threads, and then give each thread the appropriate offset and go off to the races. And some people, in fact, do that because they don't like compilers. Some of my colleagues who are dealt with bad compilers do that. Entry to and exit from parallel regions entails a barrier. This is really important, okay? Don't just go, oh, here's a parallel thing, stick a parallel for around it, and then once you leave scope, it'll close that parallel region, and then do that over and over again, okay? Unless something magical happens that I don't know about, you will basically be barriering between every single thing. There's no reason to barrier unless you need a barrier. And in fact, I will argue that a barrier is actually never an appropriate synchronization construct unless you know that you have a certain all the dependency of threads. So, don't, if you want to synchronize to protect something or to rendezvous, don't just close and open a region. There's an OpenMP barrier you can use if you really want to use it. And more likely, what you really need to do is what we'll see later, which is OMP single or critical, which just says, do this on one thread or do this in a thread-safe way because it needs to be. So if you need to, go right to a common block or a common variable or do anything that's not thread-safe, don't go in and excise that from parallel regions. Keep it in a parallel region and serialize for it correctly. And we'll see why in just a second. So here's parallel loops, and you should just run the code and look at the output. But this basically just shows you what the work distribution is. So there's schedule static, schedule dynamic. This gives hilarious results on my Mac. It basically runs like almost everything on thread 6, or picks one thread and gives it all work, so it's terrible. And then there's schedule static with chunk size 1 and then ordered. So ordered says the loop has to execute as if it was serial ordering. Sometimes this is really useful for debugging. Anyways, you should look at the results. It'll be useful. Now, so we talked a little bit about this already, but when does static versus dynamic scheduling make sense? Can somebody give examples, not referring to previous examples? So BLAS. Do you think BLAS should be static or dynamic?
Static.
Yeah, so the cost of the operation inside of a do loop in BLAS is pretty much homogeneous, other than the memory access time. You're basically doing a multiply or an add or a store or whatever. There's no real variation. Now, I guess because I'm lazy and I don't know any better example, the dynamic scheduling, of course, makes a lot of sense when you have load imbalance. So in the two electron integral case, you say dynamic. Dynamic has overhead. There's a scheduler running, and therefore you shouldn't do it if the computations are really, really cheap, because the overhead will be significant relative to that. So if you have, for all, and then you call foo of I, if foo actually takes like, a 1/10 of a second, put a dynamic scheduler on that, because the 1/10 of a second for foo will cost a lot more than the runtime overhead dynamic, and if you don't really know whether or not foo is completely homogeneous in its execution time, you'll get better load balance that way. And the tutorial has a full list. You should try them all. There's runtime, guided, and some other things like that. The best thing to do is just try these on machines you care about, because the implementation details will affect the various performance. Okay, so dealing with race conditions in OpenMP. So OpenMP is shared memory. You can have race conditions if you're storing the same data. So, some people will go in and they'll say, okay, I know that I spend 90% of my time in doing couple cluster and matrix multiply. So assuming you didn't call laws, you could go in and put OpenMP around all your matrix multiplies, not touch any other code. There's something called Amdahl's law, which I won't go through, but it's very, very simple. It's absolutely critical that you guys understand it. You should read about it. I'm sure Wikipedia actually has a great exposition on it, or we can talk about it this afternoon. If you do that, you get killed by Amdahl at some point. Amdahl personally won't kill you, but your performance will be very, very bad, and everyone who operates your computers for you will probably at some point come after you. And the reason is that, if you put OpenMP parallel around 90% of your code, and then you run on a ridiculously fast multi-core machine, all that 90% goes down, starts creeping down and down and down, and that 10%, that just stays there and stays there and stays there, and in the limit of infinite threads, that 10% becomes 100%. And so you cannot go any faster than, it's whatever, you can't go faster than the slowest, whatever. You cannot parallelize things that aren't parallel. So you will run out of parallel efficiency when you run out of things to parallelize. And then, so OpenMP makes it really easy to write fork join programs which are basically serial and then fan out and do parallel work every once in a while. That doesn't mean it's a good idea, okay? This is the reason I hate OpenMP, is they make it really easy to do the wrong thing. But of course, sometimes you have crappy legacy code that you just need to do the best you can, okay? You are not required to write terrible fork join programs. You should only do this if you are modifying someone's code who has like gray hair and you just don't want to deal with it. If you're writing your own code, don't do this. The best use of OpenMP should lead to, in my opinion, one parallel region, the entire program. The entire program should, just like you do MPI init, MPI finalize, which we'll talk about tomorrow. You start with one init and you end with one finalize. You should have OpenMP parallel 4 at the top, and then you should go out of scope at the bottom, and in the middle, if it's not parallel or it's not thread safe or whatever, there's constructs to fix that. So, and this is the take-home message. You want race-free parallel code. That's your goal. Your goal is not occasionally parallelize a little bit of your code because it makes it run, faster on some machine. Okay, race-free parallel code is the goal. Okay, so if you have things that you need to make run in a thread-safe way, there's some constructs for this. So master, single, and critical mean 3 different things. So master means run it on the master thread, thread 0. Single means run it on one thread, but you don't care who. So master and single really don't make a huge difference, other than there's some optimization if you always choose master, or in some weird cases with networking and things like that, it might theoretically be better to run it on master. Like if you're on a Cray machine, a dual socket Cray machine, and the network hangs off of one socket, and you need to serialize for OpenMP, which we'll talk about that tomorrow or Wednesday morning, you probably want to use master rather than single to guarantee that you get the core 0 on socket 0 that's connected to the NIC. But it'll take you a while before you ever notice anything that affects that. And then there's critical. Critical is different than single. Critical says this is a critical section. Do this block non-overlapping with other threads, but all threads do it. So when you run it, you will see the difference. So this is a way of saying I need serial execution, and this is a way of saying I need serialized execution among threads so that they don't do something bad. Okay, so if you need to write to a file, and all your threads can write to the file, but they can't be writing at the same time, then you put critical around it. If you only want to write the file from one thread, then you do single or master. Okay, these are sufficient to unparallelize your code as necessary.
Hey, Joe?
Yeah.
Just for my own clarification, so on the top one, the master thread runs it. In the middle one, any old thread runs it.
Yes.
So the top two, just one thread went through that code.
Yes.
But in the bottom one, everyone goes through it, they're just doing it one at a time.
Yes.
Okay.
And I in fact, wasn't entirely sure about that until I ran it. So that's another important life lesson. Trust absolutely no one. Run code, and then you'll know. Read and run code are the two. In fact, I espouse another philosophy. It's painful, and people will not like you for it. Don't read documentation. Read source code. Documentation is wrong all the time. It's really hard to make source code. I mean, source code can be wrong, but it will be correct in that it will read wrong and run wrong. So I actually do this. I never read people's docs. I go in and I try to build their code. If it doesn't work, I then read the source and figure out what they really did, not what they told me they did. And frequently you find that, oh, the docs are dated from like 2007, and this source file was modified last week. How do you possibly know that the docs are right? So in the case of things like MPI and OpenMP, really you'll learn a tremendous amount by just running lots of code. Okay, so this is the thing I was trying to illustrate before. This is fork join. This says, hey, we're marching along, we're in serial, hey, we're gonna fan out, we're gonna do something expensive in parallel, and then we're gonna close that parallel region, we're gonna go march along in serial, then we're gonna fan out, we're gonna do some more parallel stuff. And this says, I actually wanted to write a serious parallel program, so I did, except right here, something needed to happen that wasn't thread safe for whatever reason, so I pinched it, and I made sure that it only ran on one thread. And I can tell you, this is sort of biased because of the way that I'm a crappy artist. But this might actually be semi-correct in the sense that the amount of parallel performance you will get out of the code is much higher. And there's a lot of advantages to doing this. And this is in fact how MPI works. So MPI, when you call MPI init, from the moment you call MPI init, everyone is running in parallel. And you're either going to run replicated or distributed. Global arrays is the same way, and it's a very powerful concept in global arrays that everyone is going to compute the same thing. So if you have little temporary stack variables, automatic variables, whatever, every thread or every process is always going to own them because when in doubt, they're just all going to compute them, and then you enter these parallel do regions, and then you actually start distributing work. And that means that you've got sort of your local state is always there, and you don't have to go in and broadcast from some root, or in terms of memory locality and things like that. MPI is actually much more NUMA friendly because every process has its own copy of the data, which will sit with some affinity to that process, or the thread that executes, the hardware thread that executes that process. Whereas OpenMP, if you do this fork join style, you'll have all the data hanging off of the master thread, and that can actually create NUMA problems. All right, so just illustrating that picture in terms of pseudocode. So, over here, we've got, okay, run some parallel stuff because the thread's safe. Did I do this right? Oh, okay, no, here we go. So we open a parallel region. So now we're running in parallel. We do stuff that's thread safe. It might be, it's replicated here because we're not distributing it at all. Then we hit something we need to be single threaded because it's not thread safe. Then we do parallel for, and we do some loops. Then we do parallel sections. We do some task parallels and stuff like that. Then over here we have the other version, which is you do your thread unsafe stuff, you march along, you do parallel for, and then you exit that parallel region, then you do more thread unsafe stuff, and then you do your parallel for. So this is sort of the legacy view, and this is sort of the modern view. I'll write a test program this afternoon in time to open and close, because I'm actually curious how bad it is. It actually is bad enough that it matters. On Blue Gene Q, not Argonne, but Livermore, they have a lot of multi-physics code written by, massive code teams, and each team is writing different physics. And they want a thread, but the code teams, it's not practical for them to coordinate at a level where they would sort of fuse their threading models. So what it means is physics A goes into threading, and physics B goes into threading, and C goes, and they're all sort of fanning out, doing fork join over and over again inside these little physics packages. And it turns out because of that, they actually required IBM to do really fancy hardware optimizations to make OpenMP parallel open run ridiculously fast in a way that's, when the same requirement was suggested to another vendor, they were basically like, you've got to be kidding, we will never do that. So, so it is significant enough that, in fact, Blue Gene has literal silicon designed to make this type of thing run fast, because it becomes a bottleneck when you have to do very fine-grained threading and go in and out a lot. But I'll time it over back and see what happens. I'm part of the performance engineering team, and so I do a lot of stuff with performance analysis. So I feel obligated to tell you that lies to analyze in performance analysis, and so a lot of you may ask people. I don't know if you've heard this. Anybody ever told you that MPI is better than OpenMP? I mean, in terms of parallel performance? Because I've heard that and I've read that, and it turns out, I mean, this is total BS. But it happens to result from the differences in the two models. As I said, I think multiple times now, I guess, MPI is parallel by default. You're running SPMD from the get-go. OpenMP is going to be serial by default, and then you're going to only fan out when you're in parallel region. So that means that MPI is going to be executing in parallel more of the time. Now, it doesn't necessarily mean that it will do more distributed parallel stuff, but just as a matter of necessity, because people write MPI knowing they're always running in parallel, they then parallelize a lot more of their code. Whereas OpenMP, people just tend to put parallel for around the critical points in their code. So you end up with comparing an OpenMP version of a code where 75% of the code runs in parallel to an MPI code where 90% of the code runs in parallel or something. Then the other thing is that MPI, as a result of not being shared memory, requires you to actually do a data decomposition. You actually have to make a data structure which can span multiple processes. Well, OpenMP allows you to be lazy and just stick everything, if you want to do parallel matrix multiply on MPI, you've got to block up the matrix and give tiles to different processes. And then you have to exchange them or BCAS or whatever. With OpenMP, you just say, oh no, I've just got one big array, no tiling, whatever. And it turns out that that's actually a really bad way to get good scalable performance. And if you took the MPI code, you backport it to OpenMP, and you actually say, no, I'm going to do a block-based task parallel algorithm in OpenMP the way that matches the MPI one, probably run a lot better. It's this exact same thing as Robert talked about with backporting CPU stuff to CPUs for vectorization and fine-grained concurrency and all these things. It's exactly the same thing with MPI and OpenMP, that when MPI has actually been around a little bit longer, but adopted a lot more. People are always sort of talking about, oh, I have MPI only and I want to add OpenMP, or I want to, hybridize or whatever these things. And they start doing that work, and they find that their MPI only usually runs better. And it's just because they have done a substantial amount of work to make their MPI code run right, and they're not properly adapting their OpenMP in the same way. I'm not necessarily telling you the OpenMP is great. I'm just saying that it gets beat up on a lot for totally nonsensical reasons, because people aren't thinking about the nature of the comparison. So OpenMP should always beat MPI apples to apples. because there's, if you think about it, they're both ways of getting parallel execution. They both create hardware thread teams. In one case it's an OS process, in another case it's an OS thread, okay? So threads are lighter weight than processes in the operating system. Load store is faster than anything that MPI can do. MPI can do magic as much as it can with load store, but it has to at least do one copy for inter-process send receive, and other things like that. There's no way that OpenMP can be more expensive than MPI. So therefore, if you see the opposite behavior, it is because it is not a fair comparison. So, anyways. So I was alluding to this before. So this is the effect of NUMA. So this is a program that will be in our repo. You guys will see it this afternoon. What this program does is nothing more than allocates an array, zeros the array, and then sets the array to I, which is the loop counter cast to the double. So it's just trivial data parallelism, setting to 0 and then assigning. Version A does the zeroing in serial, and version B does the zeroing inside of parallel 4. And you see here, for a little bit, it doesn't make a darn bit of difference. And then you see, as you hit 10 million elements, you see, I don't know, what about 30% performance difference, 40%, gets maybe almost to a factor of 2, and then now it's more like 10 or 12%. So why is this? So this is true on a dual socket multi-core machine. It is not true on my laptop. And the important thing is, I don't know, I didn't look at all the slides, but you see about hardware architecture, you know what a dual socket machine looks like. You have 2 CPU sockets, there's a bus, and then there's DRAM. But the DRAM banks hang off of memory controllers, and depending on your AMD or QuickPath or HyperTransport and all these things, but some of the DRAM is closer to one socket than it is to the other. And Linux has this thing called first touch page faulting. So what that means is, so malloc isn't really allocating, it's just reserving memory. So the malloc basically says, I promise that whenever you actually want to use it, there will be this memory. The operating system sits around and sets some data structures up, and then you actually go in and zero that thing. What zeroing does, it goes in and faults the page, and you have copy on write. So basically what will happen is you take a 0 page from the OS and you just copy it to the physical page, and it becomes memory-backed, physical memory-backed storage. Well, when that happens, it is being faulted by the thread that is doing that. And so those physical pages of memory are hanging off of the core, or the socket, that is where the core that is faulting the memory is actually running. So that means when I zero out in serial, all of the memory is hanging off of the DRAM on socket 0 of 2, okay? When I do this in parallel, I will now stripe them across the banks so that half of the memory will be hanging off of socket 0 and half of the memory will hang off of socket 1. And that makes a difference in a NUMA machine where socket 0 can read its own DRAM faster than it can read the DRAM on the other side because it has to hop across the bus a little bit farther, okay? And this is what our crazy retired nuclear physicist found, because he's extremely obsessive about performance. He was running on our dual socket Intel machine, and he said, why is it that my thread scaling is bad, and this and this and this? And it turns out that he's a Fortran 90 guy. He's calling it allocate, and he's just doing allocate up here, and then he was zeroing it out because memory. Who thinks zeroing memory is a bottleneck in your code, right? It doesn't. It's going to take like 2 seconds, and then you're going to run for 2 hours. Who cares? Why would I put a parallel 4 region around this? So this is sort of another reason to parallelize the whole portion of your code. He was parallelizing the flop intensive portion of his code. Green's function Monte Carlo is really, really floating point intensive. And it turned out that he's actually memory bandwidth limited in some parts of his code, and he was getting hosed by the system because he was faulting all the pages off of one socket. And so when the threads fired up on the second socket inside of his compute intensive region, he was paying a penalty. He was also losing some of the bandwidth, because you actually get more bandwidth if you run out of both banks and get both memory controllers than if you try, one memory controller has theoretically half the bandwidth of two memory controllers. So this is an important thing that you can end up hosing yourself with if you're not paying attention. Something as basic as zero memory, and this is important if you're doing the right thing right, and you're not re-implementing the C standard library. You're probably using memset, or maybe you use calc because you want to just do malloc and zero. Well, last time I checked, calc and memset weren't multi-threaded, so you probably shouldn't use those unless you want to see this behavior. So that means you may in fact actually have to write your own. I mean, I have my own, little collection of toys like OMP memset, which is memset only written with OpenMP so that I can avoid this behavior. One of the other things, of course, is maybe you're not running stupid vector parallelism like I was for this silly test. You might actually need to think about how you map your data to memory if it's complex. If you're going to run task parallel, like let's say you're going to do a block sparse tensor contraction, you might want to write your zeroing code so that the blocks always get allocated to one socket or the other, so that they can hopefully get picked up by the thread that owns them, or at least, at the very least, come off of one socket, one bank or the other. This is a problem, of course, for dynamic load balancing, and something we see with global arrays. Global arrays doesn't schedule with any sort of affinity because it's a dynamic load balancer. So it gives a perfect load balance, except it doesn't really allow you to exploit it allows you to exploit process locality, but not sort of machine locality. You get the exact same thing in OpenMP. If you do OpenMP schedule dynamic, OpenMP doesn't think about the fact that you actually faulted the memory on the other core. It doesn't say, oh, I know that memory is closer to those cores, I should attach those threads. So this is a reason to avoid something like parallel 4 and actually implement your own sort of task parallel thing where you actually say, oh, I'm going to assign these tasks to these threads and then have some data affinity in the memory so that you can exploit the hardware a little bit. And that's actually the end. So, questions? Yeah.
Yeah, actually, can you tell anything about the data affinity in OpenMP? I heard that they develop such tools in the next version, like standard.
So OpenMP has the accelerator, or there's a TR1. There's some stuff for that, but the problem is that OpenMP can't specify operating system behavior. So, and they don't specify a memory allocator. So until they standardize an OpenMP memory allocator or an OpenMP memset, we won't really solve these problems completely. And there is, in fact, as far as I know, no standard way to query this information. If you're really insane and you are willing to be Linux dependent, which is a perfectly reasonable thing to do in today's day and age, there's a way you can look up like the physical memory map in the /proc, but you probably have better things to do with your time. And inventing better algorithms for quantum chemistry is probably worth like 5,000 times more performance. So.